Assalamualaikum and a very blessed good morning to all the viewers. I am one MAIDZATUL NAZIFA BINTI ROSLI as one of the group members. Our group will be telling you about the chemistry kitchens and how that's it related to us. First, let's go to the introductions. Actually, there are many things which related to the chemistry. For example, like in the kitchen itself, I can set as an example salt, which come from the sodium chloride. So there are many things and activities which are related to the chemistry, and our group today will be tell you about a few examples and activities in the kitchens which are related to the chemistry. Let's go deep into it. So these are a few examples and activities which in the kitchen which are related into chemistry, which are gas stove, which related to the thermochemistry and what type of reaction involved, baking, which involved in ionic equilibrium, but how does it related between both of them, ice cube, which is involving in phase equilibrium, but how can it occur? And these all three examples will be presented by other members.
Now, let's take a look on our first chemistry application in the kitchen, gas stove. I am sure we all know what is gas stove, as you can find it in most houses. Gas stove applies combustion as it utilizes the exothermic reaction to cook our daily food. How gas stove actually work its wonder. As its name, gas stove use certain gases to be combusted and create a flame. We have compressed natural gases CNG, liquefied natural gases LNG, and liquefied petroleum gases LPG. However, in Malaysia, our cooking gas is usually produced from LPG, which is mainly consists of propane. LPG is the most widely used due to its advantage as a highly efficient cooking fuel. It undergoes complete combustion, undergoes rapid combustion, has an excellent heating capacity, and is environmentally friendly. How can we relate the combustion of LPG with what we learned in FAD1007? Yeah, it used the thermochemistry concept. The combustion of propane gives out the chemical equation above, where propane combusted with oxygen will produce carbon dioxide, water, and heat. Therefore, we can conclude that the combustion of propane is an exothermic reaction, which it releases heat. The heat is used to cook raw food and prepare dishes. If we calculate the enthalpy of propane combustion, it is equal to the enthalpy of carbon dioxide formation. If propane undergoes complete combustion, it will produce blue flame, while if it undergoes incomplete combustion, it will produce orange flame. The combustion of propane is an irreversible chemical change.
Now, me, ZULMAJDI, and my friend AKASHA will be discussing on how we could relate baking situation to what we have learned in chemistry. Here, we are focusing on baking soda and baking powder in relation to the topic of ionic equilibria. While most of us are used to using baking soda while helping our mother to bake cake during Hari Raya, do you know exactly what it is made up of? Baking soda is actually a compound chemically known as sodium hydrogen carbonate with a chemical formula of NaHCO3. It is a salt with a weak basic nature. Therefore, when it is dissolved in water, it forms an alkaline solution with a pH of around 8.3 to 9. Typically, baking soda is used as a leavening agent for increasing the volume and lightening the texture of baked goods, such as cake and cupcakes. The mechanism is pretty simple, in which baking soda or sodium hydrogen carbonate reacts with an acidic ingredients in the dough or the mixture, such as buttermilk or lemon juice, to undergo a neutralization reaction. During the acid-base reaction, CO2 is released as a product, creating numerous air bubbles, making the texture of the cake fluffier. When discussing about the basicity of baking soda, we have three different theories which we will discuss in the next part. The first acid-base theory is the Arrhenius theory by Svante Arrhenius. According to Arrhenius' theory of acid and base, a base is defined as a substance that dissociates in water to produce hydroxide ions OH- in aqueous solution. The next theory is introduced by Bronsted and Lowry and known as the Bronsted and Lowry theory of acid and base. In this theory, a base is described or defined as a proton acceptor which becomes a conjugate acid when it accepts a proton or a hydrogen ion. And last but not least, Another scientist named Gilbert and Lewis proposed his own theory. According to this theory, a base is defined as an atom, ions, or molecule that donates a pair of electrons to form a coordinate covalent bond. However, among all of these theories, which one is the best to describe how baking soda behaves as a base? The answer is no other than the Bronsted and Lowry theory. In fact, do you know that despite being a base, baking soda also can act as an acid too?
This is because bicarbonate ion is an amphoteric species, which means it can act as an acid or even a base. Bicarbonate ion depends on what it reacts with. For example, when bicarbonate ion react with OH- or hydroxide ion, it will become an acid. And also, when bicarbonate ion react with H2O+ or hydronium ion, it will become a base. Now I'm going to talk about the baking powder. Baking powder is also used as a leavening agent. It consists of baking soda, weak acid, and also filler. So as you can see here, it consists of baking soda, which automatically means that baking powder is not baking soda. And then, baking powder can be used without acidic ingredient. It can also act as a buffering agent, same as baking soda. So to relate the baking soda and also baking powder with the topic ionic equilibria, we can see here that both of it can act as a buffer to maintain pH balance of a food. Automatically, it can also act as an antacid in the human digestive system when we consume the food that contain baking soda and also baking powder.
Another common situation that we often see when we are in the kitchen or when we are drinking water, especially ice water, we will see that the ice will actually melt. So why does this ice melt? So water is involved in a single component system, but they exist in 3 different phases in which they are solid, liquid, and also vapor. So this is the phase diagram for water. It involves 3 different phases and represented by 3 different curves. So the first curve is the OZ curve. It is the vaporization curve or the liquid and vapor boundary. And at point Z, it has a critical pressure of 218 atm and temperature of 374 degrees Celsius. So this curve represents vapor pressure of liquid at various temperature. And at 1 atm, the corresponding temperature is 100 degrees Celsius, which is the boiling point. And at point Z, it has a critical point. Okay, so critical point is basically the point in which liquid and vapor has the same density, so they are difficult to be distinguished. So moving into the next curve, which is the OY curve. Okay, it is the solid and liquid boundary or the fusion curve. So at point Y, it also meets the critical pressure of 218 degrees Celsius. And along the curve, the 2 phases of solid ice and water will coexist in equilibrium. And at point B here, the pressure is 1 atm and the corresponding temperature is 0 degrees Celsius. So from this curve, we can see that the melting point of ice will decrease when the pressure increases. So the last curve is the OX curve or the sublimation curve. It is the solid and vapor boundary. So at this point X, it has a temperature of absolute zero temperature, which is negative 273 degrees Celsius. It depicts the vapor pressure of solid ice at various temperature. And in equilibrium, the 2 phases of solid ice and water vapor will coexist. And lastly is the triple point. What is basically the triple point? It is the point in which all the 3 curves will meet. It is the only condition in which all 3 phases will coexist in equilibrium with one another. In previous phase diagram, solid-liquid equilibrium has a negative slope. So firstly, when pressure of an object is increased, volume will become smaller, so density is higher. So in this diagram, we can see that liquid water is more compact between each other compared to ice molecules. So basically, ice is less dense than liquid water due to large empty spaces existing between molecules due to the ordered 3-dimensional network of hydrogen bonds in ice molecules. So melting temperature will decrease with pressure. So water molecules are farther apart in ice than in liquid water. Thus, ice has a lower density than liquid water. So So that is all from our group. Thank you.